Hello everybody, welcome to another video lesson. Now we're looking at geometric series. This video, we are going to find sums of finite and infinite geometric series. So let's hop right into what a geometric series is. It is just a sum of terms of a geometric sequence. And again, we denote that with S sub n, which we've seen before. So again, if I have my sequence 2, 4, 8, 16, my series would be 2 plus 4 plus 8 plus 16. So finding the sum of a finite series would look something like this. I'm going to write out the sum of a finite series as a sub 1 plus a sub 1 times r plus a sub 1 r squared, okay, plus, and then all the way at the end we have a sub 1 r to the n minus 1. So we get this from our formula that we used in the last video. Now what would happen if I were to multiply everything by r? So I multiply both sides of these by r. Now can we see how each one of these terms would kind of shift to the right one? So instead of a sub 1, I would have a sub 1 times r. And instead of a sub 1 times r, I would have a sub 1 r squared. So everything kind of shifts over a little bit. And at the end, instead of having a sub n, r to the n minus 1, this would actually be a sub 1. It's a 1 there. We would have another term here, which would be a sub 1 r to the n power instead of the n minus 1. We end with r to the n. Now again, I'm going to do something a little weird. I'm going to subtract these two equations. And when I do that, I get s sub n minus r s sub n. I get a sub 1 on this side. But now we can see that since I have the same terms on the top and bottom and I'm subtracting these two, those are going to start canceling out, right? All these terms are going to start canceling out. So all I'm left with really is a sub 1 minus a sub 1 r to the n. And if I were to factor out my s sub n on the left-hand side and factor out a sub 1 on the right-hand side, and then divide both sides by 1 minus r to solve for s sub n, I would get this expression right here, which is our formula for a finite series. Now, I'm not going to devise or derive this second formula, but if you manipulate this first formula a little bit, you can arrive at this second formula right here. So both of these can be used depending on what information you're given. Okay, so now infinite geometric series, finding the sum of an infinite series here. Let's think about this. If I have my sum and I have our formula here, if my common ratio is greater than 1, or the absolute value of that common ratio is greater than 1, then what happens to this term here? This r raised to the n power, this term right here. Well, that number is going to increase infinitely, right? Because if I have some value, say 2 is greater than 1, right? And I raise it to the second power, well, that's 4. But if I raise it to the millionth power, it's something really, really, really big, right? It's going to increase infinitely. But what happens if r, the absolute value of my common ratio, is less than 0? What happens to our r sub n then? That r to the n is going to approach 0. Think of it like this. If my r is 1/2, and I raise that to the infinity power, well, that's going to be 1 over 2 to the infinity, because 1 to the infinity is still just 1. And as this number, my denominator, gets larger and larger and larger, this value approaches 0, right? So for my sum, this value here, r raised to the n, is going to go to 0 if we have an infinite series. Again, if r is less than 1. Only if r is less than 1. So then my final formula would be my sum is equal to a sub 1 over 1 minus r. Okay, so those are our concepts. Let's get into these examples. First one, find the sum of the first 11 terms of our geometric series. So I've got our series here. We need to find out what our common ratio is. And we can do that by taking the quotient of our consecutive terms, and we find it's going to be negative 3.5. So our formula says r is negative 3.5, a sub 1 is 7, my n is going to be 11, because I'm looking for the first 11 terms. So I can go ahead and just plug these values right into my formula. Okay, and when I calculate that out, just plug that right into a calculator. Be careful with your parentheses with this negative 3.5, and you get a very, very large number. Okay, example 2, geometric series. Finding the sum of the first n terms of a geometric series. now. Okay, so I'm given a sub 1, and I'm given a sub n, and I'm given my r value, and I need to find the sum of the first n terms. So now we want to use our other formula, our second formula for this. Okay, now I have values for, again, a sub 1, a sub n, and r, which is what we have here, here, and here. Okay, we have two r's in there, but really there are no more unknowns, right? So I can just plug this directly into a calculator, and I get 104,856 for my sum. Okay, we can also see these in sigma notation. It's always good to get some practice with sigma notation. So my n now is going to be, again, 11 minus 4 plus 1. Plus 1. Don't forget that plus 1 in there, and we reviewed that in a previous video. So my n value is going to be 8, and is 8. Now, whatever is being affected by my n, by this dummy variable n here for my sigma notation, that is going to be my ratio, right? That is what we are multiplying here. So if my ratio is 0.5, what is my a sub 1? Well, my first term here, not necessarily a sub 1, but my first term that we're going to start adding is going to be when n is equal to 4, right? So let's plug that in when n is equal to 4, because that's my first term, and that's going to give me 120 times 0.5 raised to the third power, and that's going to be 15 when you plug that into your calculator. So now my S sub n formula here, I have everything that I need, and I can just plug these in, and I get that S sub 8, since there are 8 terms here, it's going to be 29.8828. Right now we have infinite geometric series here. If possible, find the sum of the series. Now, if you take a look at this, this might seem a little bit fishy, right? Because when I take the quotient of my individual terms, or my consecutive terms, sorry, I get 0.75 for the first two terms, but for the second and third terms, I get 0.667, which is not good, right? Because these need to be the same value here. So we actually don't have a geometric series. Instead, we can see that we have a d value of -5. We actually have an arithmetic series. And for an arithmetic series, unless my d value is equal to 0, so in this case it's not, right? It's -5. Then our sum does not exist. So an arithmetic series with a d value with anything other than 0, if it's an infinite series, that sum does not exist. All right, now let's take a look over here. We have another infinite series. This one is geometric, okay? However, now we're infinite instead of having an end value. Our end value is actually infinity. But our r is 0.8, which is less than 1, so that's okay. We're going to have some sort of sum here. So a sub 1, I just plug in 1 for my n value, and that's going to give me 120 times 0.8 raised to the 0 power, which is equal to just 120. So my sum is a sub 1 divided by 1 minus r. I have my value for r. I have my value for a sub 1. I can plug that into a calculator, and I'll get a sum of 600. All right, guys, that is it for this video. Good luck with your practice.